At the Institute of Particle Physics Phenomenology in Durham, we study the fundamental building blocks of our universe. These are particles that are unimaginably tiny and behave in complicated and sometimes confusing ways. As with any other form of science, we test our understanding of particle physics by developing an idea, or hypothesis, and carrying out experiments to test whether this idea is correct. But how can we study particles that are too small to see even with the most powerful microscope? In fact, how can you understand any experiment where you can't see exactly what happens in it? One solution is to use computers to simulate the experiment and compare with the real-world results.
Let's forget about particle physics for a moment and look at a simple experiment that demonstrates the importance of computer simulations. If we drop a ball down a Galton board, it will bounce off the pins and follow a random path to one of the tubes at the bottom. We can't predict which tube a ball will fall into, but we can work out a probability for each tube. Dropping one ball down is equivalent to running this experiment once, and we don't learn much. We need more information, so we drop many more balls down and study the pattern formed in the tubes. We can see that there are more balls in the central tubes than the outer ones, in a shape known as a bell curve or normal distribution. We now have an answer to our original question. The balls are more likely to fall into the middle tubes than the edges. This is because, to land in an outer tube, every time a ball hits a pin, it must go the same way, so there is only one path that it can follow. For a ball to land in one of the middle tubes, there are many possible paths, and so there is a higher chance that a ball will end up in the middle tubes. With this Galton board, however, we can't see all the pins. How would we know if there is some sort of obstruction in the way? Or what shape that obstruction is? We have to work this out based only on the shape the balls create in the tubes. Again, we need to drop as many balls down as we are able to. We can look at the pattern and we may be able to understand some basic properties of the obstruction, for example, whether it is symmetric. To understand more though, we turn to computer simulations. Recreating the experiment as a computer program allows us to model what is behind the door. In the case of our Galton board, we have 5 different options. Running each option gives us a pattern similar to the shape of the balls in the tubes. By comparing the patterns, we can determine which shape we think has been placed in the Galton board. The patterns may not match exactly, but running both the experiment and the simulation with more balls will improve the results, and we can be more confident with our prediction. Of course, there is also always the chance that it is a completely different shape altogether, but it may only be with a lot more data that we would realise this.
The Galton board is a simple example of a general principle. Often in science, we are confronted with data that has some randomness in it, and we want to find a hidden order, a model that explains the data. This model can be equations that not only describe the data, but also predict the results of future experiments, or an explanation in terms of physical objects such as particles. Throwing a ball in the Galton board could represent a collision in a particle accelerator, and the hidden shape that we want to uncover would be similar to the existence of a new particle whose presence affects the outcome of the collisions. This is what happens at the Large Hadron Collider at CERN. To analyze results from the LHC, a number of programs are being used to simulate the outcome of particle collisions. 2 of the main computer programs used for this, called Herwig and Sherpa, are developed here at the IEEE. The work we do here is all about finding answers to fundamental questions, such as, what are we made of? And it is exciting to be working right at the edge of our current knowledge. We don't know how new discoveries, or the technology we develop, will find their way into everyday life, but there is a long history of seemingly unusable discoveries becoming central to our lives.